Okay, what this shows you is, so on that string, so let's go back to the string. So here's this wave traveling in the string. It turns out that the velocity of this disturbance will depend on the properties of this medium, of course. It turns out if you use a heavier string, you find that you connect a heavier string to the same oscillator, and what you find is the velocity of the wave is slower. Okay? If you increase the tension in the string, the velocity of the wave is faster, okay, is higher. So, and that's what this expression gives you. So for the velocity of a wave on a string, the velocity is given by the square root of the tension divided by the mass per unit length of the string. Mass per unit length is how much, what is the mass of 1 meter of the string. Okay, so the velocity of the wave is dependent on the tension and stuff like that. So if you quadruple the tension, if the tension increases by a factor of 4, the velocity increases by a factor of 2. If the weight mass per unit length decreases by a factor of 4, the velocity decreases by a factor of 2. If the mass increases by a factor of 4, the velocity decreases by a factor of 2. All right. Now, what we will talk about is we know that all waves carry energy. We've said that. Okay. And so now we'll look at the energy distribution in a string. Okay. So here's a snapshot of. So here's this string, and here's this wave traveling on the string. Here we take a snapshot of that, and here is this snapshot. Okay. Now you see, so think of the string as made of a stretchable material, a rubber band. Okay. And right at the top there, so the string is not stretched at all. And you know, if you stretch a rubber band, that's where you have that's when you store potential energy. Okay. So there is no potential energy stored here. And here the string is stretched. So the potential energy is the most here. And of course, it's going the fastest at this point. The string is oscillating. So potential energy and kinetic energy are maximum at the same point, at the same location for the string. Okay. And here at this point, the string is at rest. So potential energy and kinetic energy are at 0 there. All right. So the rate of energy transmission. So what we're interested in is we'll stand at a location. As this wave travels, we are interested in how much energy is being transported per second. And that is the power. Okay, so that's rate of energy transfer. So the average power transmitted down the string is 1/2 mu v. Mu is a property dependent on the material. String velocity depends on the material. And omega, the frequency, and A, the amplitude. See, these two depend on the external driver. They depend on the driver. You can change the frequency of that and the string will vibrate at that frequency. Okay. So the rate at which energy is transmitted is 1/2 mu velocity times frequency squared times amplitude squared. Okay. So now what we're interested in is the following. So here is a system that's evolving in time, and we're interested in modeling the behavior of this system mathematically. Okay. And you saw that generally when you model the behavior of a system, what you end up is with a differential equation. Okay. And it turns out that okay, let me add. So let's see, do we still have that? Okay. Okay, so Cubby. Um, okay, so so we are interested in we are interested in describing modeling the behavior of the system mathematically, and it turns out that this is described. So this is evolving in time, and things are changing with spatial coordinates. So this direction will be X, this will be Y. So this will be Y, this will be X. So here's a snapshot. Oops. Here's a snapshot of the wave, and this wave will travel to the right as time increases. Okay. So it turns out that the behavior of this, this behavior, the behavior of this system is modeled by this differential equation. Okay. And this is called the wave equation. So it's given by this differential equation. Del square y. Y is a function of x and t. Del x square is equal to 1 over v squared del y. Okay. So the interesting thing about this differential equation, this is a partial differential equation. Okay, so what it's doing is it's relating a second order time derivative to a second order spatial derivative. Okay. And the dimensionality is as follows. You have x squared here, distance squared, and velocity times t, velocity times time is distance. So velocity squared times t squared is distance squared. Okay. All right. So before we go on, do you guys know what partial derivatives are? Do you guys know what partial derivatives are? And do you want me to briefly go over partial derivatives? I need for you guys to respond. If you're silent, I don't know what you're getting and what you're not getting. Okay. Hello? Okay, so, all right, so this is the wave equation. Okay, it relates the second order time derivative to the second order spatial derivative. Okay. All right. And so this models the behavior of this models the behavior of this system. Okay. So the behavior of this media is modeled by that differential equation. Okay. And it turns out solutions to this differential equation have to have this form. X plus or minus Vt. And you saw that X minus Vt was a pattern traveling to the right, and X plus Vt was a pattern traveling to the left at velocity, at speed V. Okay. All right. So now we'll learn to combine waves. Okay. So, and we encounter these situations all the time. So for instance, if you're in a concert hall and there are multiple speakers, so there are sound waves coming from multiple speakers to you, to your location. And so we want to know how different waves combine. Okay, so here we'll start off with a simple model. So here is a string, And here's a pulse on the string traveling to the right, and here's a pulse simultaneously traveling to the left. And the interesting thing about this is when they are at the same location, when they combine, when the two pulses arrive at the same location, they add up. And once they interact and once they pass each other, you see their form has not changed. Okay. So when they're at the same location, they will algebraically add. And once they interact, they do not change each other's nature. So that's the superposition principle. When there are multiple pulses at a given location, you just sum them up. Okay. And if the pulses have if the pulses have opposite signs, then when you're at that location, you see the resultant pulse was smaller than the largest pulse. Okay, this guy was smaller than the largest pulse. Okay, so anyway, and you can do this with as many waves as you want. So you can have 1,000,000 waves and combine the 1,000,000 waves at this given location. And once they interact, once they pass each other, they do not distort each other. Okay, so that's the superposition principle. So overlapping waves do not alter each other. Waves that obey the superposition principle are linear waves. Okay. Of course, there are nonlinear waves that do not add just simply like that, but we're not going to go over that. Okay, so let me show you a simulation of superposition. Okay, so here's two waves, and you can see that, so this big wave is coming from the left, right, they combine, and then once they pass each other, they have not altered each other. Okay. Now we'll talk about interference. Kavi. I'm talking. You gotta go. Okay, so now we'll talk about interference. When two positive waves interact, the resultant is greater than either one of them. Okay, and that's called constructive interference. Okay. So interference is a phenomenon of waves in the same region of space combining to produce a resultant wave. So constructive interference occurs when amplitude of the resultant pulse is greater than either individual waves. So you have two waves and the resultant wave is greater than either one of them, and that's a constructive interference. Okay, and this is destructive interference. When you have waves of opposite sign combining at a given location, then the resultant is smaller than the greatest one. Yeah, this is destructive interference. All right, I will pause for a second, and if you guys have any questions.